We're going to learn a technique called integration by partial fractions. This is going to allow us to find antiderivatives for rational functions whose derivatives can't be found using any of the other methods we've seen before. To understand why we need this method, let's take a look at the antiderivative of 5x minus 7 over x squared minus 3x plus 2. If we try to use something like substitution to solve this, letting u equal x squared minus 3x plus 2, then du would be 2x minus 3 dx. But we'll notice that 2x minus 3 is not a multiple of 5x minus 7, so we have no way to get rid of the numerator. We can also notice that none of our familiar patterns for a trigonometric substitution or the pattern required to use integration by parts are going to apply to this integrand. It turns out that with a little algebra, we can show that 5x minus 7 over x squared minus 3x plus 2 is equal to 2 over x minus 1 plus 3 over x minus 2. That means that our original antiderivative is equal to the two antiderivatives we see on the right here, and both of those are solvable with simple techniques we've already learned. The antiderivative of 2 over x minus 1 dx, using a u substitution, we can let u be x minus 1, so that du is dx. That integral can then be rewritten as twice the integral of du over u, and we know that that is 2 times the natural log of the absolute value of u plus a constant, which becomes 2 times the natural log of the absolute value of x minus 1 plus c. Similarly, the antiderivative of 3 over x minus 2 dx, using a very similar substitution, u is x minus 2, so that du is dx. This becomes 3 times the antiderivative of du over u, which is 3 times the natural log of the absolute value of x minus 2 plus a constant. So our final answer for our original problem is going to be 2 times the natural log of the absolute value of x minus 1 plus 3 times the natural log of the absolute value of x minus 2 plus some constant c. We'll look at 5 different use cases for partial fractions. First, we'll examine using it in the case of simple linear factors. Then we'll take a look at repeated linear factors. Next, we'll examine irreducible quadratic factors. Then we'll look at repeated irreducible quadratic factors. And finally, we'll examine the case where we need to use polynomial division before we can apply the method of partial fractions. Let's go back to our original example in order to see how this method works. We saw that we were able to rewrite 5x minus 7 over x squared minus 3x plus 2 as the sum of two simpler fractions that had linear denominators. Those denominators weren't chosen by accident. If we factor x squared minus 3x plus 2, we can see that we end up with x minus 1 times x minus 2 on the bottom. Those two factors become our new denominators. In other words, we can rewrite this expression as a over x minus 1 plus b over x minus 2. Our job is now to figure out what a and b are. In order to do that, let's imagine multiplying the entire expression by x minus 1 times x minus 2. When we do that, the left-hand side becomes 5x minus 7. Then we end up with a times x minus 2, because the x minus 1s will cancel, and b times x minus 1. This equation here gives us two ways that we can find values for a and b. The first method we're going to call comparing equivalent coefficients, or comparing coefficients. To do this method, what we're going to do is multiply out the right-hand side. So there we get 5x minus 7 equals ax minus 2a plus bx minus b. We'll group like terms on the right so that we get a plus b times x 2 times a plus b. We're now going to recognize that the coefficient of the x term on the left should match the coefficient of the x term on the right. That gives us the equation 5 equals a plus b. Similarly, we'll notice that the constant term on the left should match the constant term on the right. That gives us another equation, 7 equals 2a plus b. Now we have a system of equations. We can use substitution or elimination to solve that. I'm going to use substitution. I'm going to replace a with 5 minus b. When I do that, I get 7. I'm going to plug that in over here. I get 7 equals 2 times 5 minus plus b. That's 7 equals 10 minus 2b plus b, giving me negative 3 equals negative b, or b is 3. We'll plug that back in over here to give us that a is 5 minus 3, which is 2. The other method we're going to use involves choosing smart x values. This is a shortcut that doesn't always work, but when it does, it's quick and handy. So the idea here is that our original expression, this entire equation right here, 5x minus 7 equals a times x minus 2 plus b times x minus 1. That has to be true for all values of x. So what we can do is pick a smart value of x that allows us to figure out what a and b are. We're going to choose that value so that one of our terms, either the a term or the b term, goes away. So what we can do first is we can let x be 2. When we do that, on the left-hand side, we get 5 times 2 plus 7. On the right-hand side, we get a times 0 plus b times 1. So we made our a term disappear, so we now have, I wrote plus 7, I meant minus 7, so 5 times 2 minus 7. That gives us 3 is equal to b. We can then make another choice, since it's true for any x we decide on. So we'll let x be 1. Then we're going to get 5 times 1 minus 7 equals a times negative 1 plus b times 0. This time the b term dropped out. That gives us negative 2 equals negative a. And we end up seeing that once again a is equal to 2. Both methods gave us the exact same answer. And so now we know, looking back at our original expression, that 5x minus 7 over x squared minus 3x plus 2 is equal to 2 over x minus 1 plus 3 over x minus 2. Let's try another example now, starting from the beginning and working it all the way through to finding the antiderivative. You'll notice that this problem and the one we just completed have something in common. When we factor the denominators, both of the factors are what we call simple linear factors. That means they're in the form x minus r, and none of them is repeated, none of them is raised to any exponent. For simple linear factors, we can use the same technique we just worked through in order to find our values of a and b and then proceed to our integration. If this weren't factored, we'd have to go ahead and do that, but it already is. So we know that we can start off by rewriting the integrand as a sum of two different rational functions, each of which has one of our factors as a denominator. So we're going to write this as a over x minus 1 plus b over x plus 2. Now we'll proceed like we did before, multiplying both sides of this by x minus 1 times x plus 2, and seeing that when we do that, we end up with the expression 5x minus 3 equals a times x plus 2 plus b times x minus 1. We'll expand out the right-hand side to get 5x minus 3 equals ax plus 2a plus bx minus b. I'm going to work through both methods again here for solving for a and b. You can obviously choose whichever one you prefer. So the first thing I'm going to do is group my x terms together. So I have a plus b times x plus 2a minus b as those terms. And now I'm going to compare my coefficients. So I'm going to notice that 5 and a plus b must be the same. And similarly, I'm going to notice -3 and 2a plus b have to be the same. 2a minus b. All right, so now we have a system of equations, and we're going to solve that. So again, we'll do a substitution as in the previous one. I'm going to say that a is equal to 5 minus b. Plug that in over here. We get -3 equals 2 times 5, parentheses in the wrong place, 2 times 5 minus b, multiplying out, we get -3 equals 10 minus 2b minus b. Moving the 10 over, we get -13 equals -3b. So b is 13. Plugging that in here, we get a is 5 minus 13 over 3. That's 15 thirds minus 13 thirds. So we get that a is 2 thirds. Trying our alternate method, remembering that in this equation up here, any x value, so in other words, if I let x be -2, I chose that because of the plus 2 in here. I'm going to get 5 times -2 minus 3 equals a times 0 plus b times -3. That gives me -13 equals -3b. So we see once again that 13 thirds is b. Then we can choose x equals 1, noticing that that's going to make this piece 0. So we get times 1 minus 3 equals a times 3 plus b times 0. So that's 2 equals 3a, and we get again that a is 2 thirds. So now we know that our original expression can be rewritten. We're going to write 5x plus 3 over x minus 1 times x plus 2 equals 2 thirds over x minus 1 plus 13 thirds over x plus 2. All right, this is useful to us because we started off with this integral. Notice if we multiply the denominator out, we get x squared minus x plus 2x, so that's plus x minus 2. And if we take the derivative of that, or if we let that be u, then du would equal 2x plus 1 dx, which is not helpful because 5x plus 3 can't be replaced. So we need a different approach, so we're going to choose to rewrite this in terms of the two expressions we just found. We can split it into two integrals. I'll move the 2 thirds out front, and we know that since the derivative of the bottom is just dx in both cases, we're going to use natural logs to solve these, so we end up with 2 thirds times the natural log of the absolute value of x minus 1 plus 13 thirds times the absolute value, or times the natural log of the absolute value of x plus 2. And then we'll add on our constant c. Let's take a look at this next example. And first, let's examine how it's different than the one we just did. So if you take a look at the factorization of this, you see that we have 1 over x minus 1 squared times x plus 3. In the previous example, both the factors of the denominator only had an exponent of 1. So we're going to have to try a slightly different approach for this one. What we're going to need to do here is rewrite our integrand so that we have 1 over x minus 1 squared times x plus 3. We'll start off similarly as before. We'll write a over x minus 1, our first factor. But now our second factor, we're going to do b over x minus 1 squared. So whatever the exponent is, you're going to have one term for every power. So if we had x minus 1 cubed, we would then add a c over x minus 1 to the third, and so on. And then we'll add our last term, c over x plus 3. And that doesn't have an exponent on it, so we can stop there. Okay, so now we are going to proceed as before. We're going to multiply both sides of this by x minus 1 squared times x plus 3. multiply all of the terms by that. And when we do that, we'll see on the left-hand side, we just get 1. On the right, when we multiply the a term by x minus 1 squared, x plus 3, one of the x minus 1's cancel, and we end up with a times the leftover x minus 1 times x plus 3. And then for the b term, the x minus 1 squared cancels, so we get b times x plus 3. And then for the c term, the x plus 3's cancel, so we get c times x minus 1 squared. All right, we're now going to proceed as before. We're going to try to match up our coefficients. So first I'm going to multiply stuff out. So I get a times x squared plus 2x minus 3 plus b times x plus 3 plus c times x squared minus 2x plus 1. Distributing, we get ax squared, 2ax, 3a, then bx, 3b, cx squared minus 2cx plus c. All right, I'm going to combine my like terms on the right-hand side. So if I look for my x squared terms, I have an ax squared and a cx squared. So that gives me wrong color. I get a plus c times x squared. I have a 2ax, a bx, and a negative 2cx. So putting those all together, I get 2a plus b minus 2c all times x. And then for my constant terms, I have a negative 3a, a positive 3b, and a positive c. So I get negative 3a plus 3b plus c. And now we can equate our coefficients. So notice on the left-hand side, I have no x squared term. So that tells me that I get 0 is equal to a plus c, my x squared term on the right. Similarly, I have no x term. So that gives me that 0 is equal to 2a plus b minus 2c. And thirdly, I do have a constant term, and that's going to give me that 1 is equal to negative 3a plus 3b plus c. Okay, now we have a system of 3 equations in 3 variables, which we're going to solve. So I'm going to notice that if I combine these two and I eliminate b, I can then use that in conjunction with the first equation to figure out what a and c are. So to eliminate b, I'm going to multiply the top equation, this guy, times negative 3. And that's going to give me 0 equals negative 6a minus 3b plus 6c. I don't need to change the bottom of equation. I get 1 is negative 3a plus 3b plus c. And when I add those together, I get that 1 is equal to negative 9a plus 7c. The b term went away. All right, I'll go back to my original equation here to bring this down here, and I'm going to multiply it by 9 in order to eliminate a. I could also choose negative 7 if I wanted. I get 0 equals 9a plus 9c. When I add those together, I see that 1 equals 16c, so I get c is 1/16. Since 0 equals a plus c, that means 0 is equal to a plus 1/16, so a must be negative 1/16. And then we can plug those values for a and c into either of our remaining 2 equations. I'm going to use this one right here. Say 0 equals 2 times 1/16 plus b minus 2 times 1/16. That gives me that 0 equals 1/8. A was negative 1/16. This should be negative, so that's negative 1/8 plus b minus 1/8. So b is equal to negative 1/8 minus, or 1/8 plus 1/8, which is 1/4. Okay, now that was a lot of work. So you might be asking yourself, why did we not just use the smart x method? However, if we look at this equation right here, come back to this right here. Remember when we used smart x's, we had to find values that would make each of the coefficients disappear. We could use x equals 1 to make a and c disappear. And we could use x equals negative 3 to make b disappear. but there isn't a way to make just A disappear without making everything else disappear. So in other words, if we use this method, we would be able to find B by letting x be 1, and we would be able to find, we would be able to find C by letting x be -3, because both the A and the B term would disappear. But there's no way to find A. So this isn't going to work, and we're going to end up having to do some of what we just did anyway. So I'm going to leave it there and just use matching coefficient method. Okay, so from here, we now know that our original integrand, 1 over x minus 1 squared times x plus 3, antiderivative is now, we have A is -1/16, so we get -1/16, 1 over x minus 1. B was 1/4, so we have 1/4, and that was 1 over x minus 1 squared. And then C is positive 1/16, and we have 1 over x plus 3 dx. All right, each of these is fairly straightforward to integrate. The one on the left and the one on the far right are both logarithms. So we're going to end up with -1/16, the natural log of the absolute value of x minus 1 for the one on the left. The one on the right is 1/16 times the natural log of the absolute value of x plus 3. The one in the middle is, we have du over u squared. If we do a quick u substitution, the antiderivative of that is negative u to the -1. So we're going to actually get -1/4 u to the -1, which would be x minus 1 in the denominator. I'm going to write that a little more neatly to wrap it up. So our final answer is -1/16, the natural log of the absolute value of x minus 1, minus 1 over 4 times x minus 1, plus 1/16, the natural log of the absolute value of x plus 3. And since we had an indefinite integral, we're going to add on plus c term. Okay, in our next example, we're going to notice that this time, one of the factors in the denominator is not linear anymore. It's quadratic. We have an x squared plus 4. So in order to rewrite something that has a quadratic, we have to use a slightly different technique. In particular, to rewrite 2x plus 7 over x plus 1 times x squared plus 4 as a partial fraction decomposition. The x plus 1 is linear, so we're just going to give that a constant a in the top and rewrite that factor. Because x squared plus 4 is quadratic, that means that the numerator we put on that fraction has to be linear. So we're going to write bx plus c over x squared plus 4. From here, we can proceed like we have been, where we're having a really hard time writing the number 4. There we go. We can proceed just like we have been, where we're now going to try to figure out what a, b, and c are by using probably a system of linear equations. So we're going to now multiply both sides by x plus 1 times x squared plus 4. And that's going to give us 2x plus 7 equals a times x squared plus 4, because the x plus 1s will cancel, and then plus bx plus c times x plus 1. Now we can multiply things out, so we get 2x plus 7 is equal to ax squared plus 4a plus bx squared plus bx plus cx plus c. Let's group our common terms on the right-hand side, so we can see that we have both an ax squared and a bx squared, which gives us a plus bx squared. We have a bx and a cx term, so that's going to give us b plus c times x. And then we have a 4a and a c term, so we'll put those together. We have no x squared on the left-hand side, which tells us then that the coefficient of the x squared term on the right must be equal to 0, so we get that 0 is equal to a plus b. We do have an x term, so that gives us that b plus c has to equal 2, the coefficient of the x term, and then 4a plus c must be our constant, which is 7. So we have a system of equations that we can use to solve I'm going to use substitution. I'm going to notice here that a is the same thing as negative b, and I'm going to replace that in my other equations anywhere I have an a. So this one doesn't have an a, but this one does. When I replace a with negative b, I get negative 4b plus c equals 7. If I multiply that equation by negative 1, I get 4b minus c equals negative 7, so that when I add that to my other b plus c equation, I see that 5b is equal to negative 5. So we get that b is equal to negative 1. We can use that back here to get that a is equal to positive 1. And then since we know that b plus c is 2, got that equation kind of hiding up there, right there. B plus c is 2, and we know that b is negative 1. That is going to give us that c is equal to 3. Okay, so now we can go back to rewriting our original expression. So we started off with this antiderivative of 2x plus 7 over x plus 1 times x squared plus 4. And our partial fraction decomposition allows us to rewrite this as 1 over x plus 1 dx. And then we're going to get, we have a negative 1x, so negative x plus 3 over x squared plus 4 dx. Now, the first of those is straightforward. That's a natural log antiderivative. The second one, substitution, isn't going to work for us because letting u be x squared, we still have a plus 3 on the top. But we know that we could split that further. So I'll just rewrite the first one for now. I'm going to split this up into negative x over x squared plus 4. And then plus 3 over x squared plus 4. We have to remember that when we have the pattern 1 over x squared plus a squared, the antiderivative of that is inverse tangent of x over a. So we can now proceed with all three of these. The first one is the natural log of the absolute value of x plus 1. The second one, if we do a quick u substitution, u is x squared plus 4, we get that du is 2x dx. So we can say that negative 1/2 du is the same as negative x dx. That makes that middle antiderivative. We get negative 1/2 times the natural log of u, which is x squared plus 4. Normally we'd put absolute value bars around that, but we have to remember that x squared plus 4 is always positive, so we don't really need them. No harm in putting them, but we don't need them. And then the last one, we've got 3 times the inverse tangent of x over 2, because our a value is 2 in that case. And then we're going to add on our constant because we're talking about an indefinite integral. And that is our final answer. Let's take a look at another example where we have an irreducible quadratic factor in the denominator. Irreducible means it can't be factored any further, because if it could be factored any further, we'd do that, and then we'd use our process for linear factors. Here, notice that we have a quadratic, 3x squared plus 1, in the denominator, but this time it's raised to the third power. So we're going to have to use a process similar to the one we used when we had a linear factor raised to a power. So in order to rewrite our integrand, we have 9x to the 5th plus 6x cubed all over 3x squared plus 1 to the 3rd. All of our denominators are going to have the cube 3x squared plus 1 in them, just raised to various powers, which means all of our numerators have to be linear. So we're going to have something of the form ax plus b over 3x squared plus 1 to the first power. Then we're going to have cx plus d over 3x squared plus 1 to the second power. And then we're going to have to introduce ex plus f over 3x squared plus 1 to the third power. So you can see the process is the same, but it gets perhaps exponentially longer when you have higher powers of higher power factors in your denominator. But we're going to proceed the same way we would regardless of the powers. We're going to multiply everything through by 3x squared plus 1 cubed. So that's going to give us 9x to the 5th plus 6x cubed equals ax plus b. That one is missing 2 copies of 3x squared plus 1, so we'll write 3x squared plus 1 squared. Then we're going to have cx plus d. That middle term is missing 1 copy of 3x squared plus 1. And then our ex plus f term contains all 3x squared plus 1 factors, so we don't have to add any additional ones there. Okay, we're going to expand this all out. So I have ax plus b. If I expand out 3x squared plus 1 squared, I get 9x to the 4th, 6x squared, and 1. I'll leave this here, the cx plus d times 3x squared plus 1 for now. All right, I'm clearly going to have to write smaller on the next line to fit this all in. So this is going to give me 9a x to the 5th plus 6a x cubed plus ax plus 9b x to the 4th plus 6b x squared plus b. I'm going to move down a line here so this next line is going to be what I get when I multiply this out. So I'm going to get plus 3c x to the 3rd plus cx plus 3d x squared plus d. And then my last bit there will be the ex plus f. We'll put that down here. So this is that blue line, and this last bit comes from that purple part over there. Just got too long for my screen. And now we'll combine our like terms. So we have only one x to the 5th term right here. So we have on the left still 9x to the 5th plus 6x cubed. But that equals 9a x to the 5th. Then let's look for x to the 4th term. So we've got a bx to the 4th, and that's the only one. Now we'll look for our cubed terms. So we've got a 6a x cubed, a 3c x cubed. That appears to be all of them. So we have plus 6a plus 3c times x cubed. Looking for squared terms now. We've got a 6bx squared, a 3dx squared. So that's going to give us 6b plus 3d x squared. And then in terms of x's, I'm running out of colors here. We've got an ax, a cx, and an ex, which gives a plus c plus e times x. And then we've got a b, a d, and an f for our constants, so we'll put those together. All right, now we only have 2 coefficients on the left, so hopefully the algebra won't be too atrocious trying to figure out what all of these letters equal. We can see that we start off with, if looking at the x to the 5th term, we see that 9 is equal to 9a, matching up this coefficient with this coefficient. So a is 1. Similarly, there is no x to the 4th term, so that gives us that 9b equals 0, so b is 0. We know that using this coefficient and this one over here, we get that 6a plus 3c is equal to 6, but a was 6, or a was 1, so 6a is 6, so we get 6 plus 3c is 6, which means c is also 0. We have 0 equals 6b plus 3d because there's no x squared term on the left-hand side. B was 0, so we get 0 equals 3d, which tells us that d is also 0. Then we have that a plus c plus e is equal to 0 because there's no x term on the left. But a was 1, c was 0. So we get that e is -1. And then lastly, our last missing one is f, but we know that b plus d plus f is also 0 because there is no constant term on the left. B was 0, D was 0. That means F must also be 0. So we have A is 1, C, D, and F are all 0, and E is -1. All right, we can use this now to rewrite our integral. We started off with the integral of 9x to the 5th, 6x to the 3rd, all over 3x squared plus 1 dx. And we know that that is ax plus b. So that's 1x plus 0 over our denominator to the first power. Whoops, I forgot to put the third power over here. And then we had cx plus d, but those are both 0. So there's no term that needs the denominator squared. And then we had ex plus f, so that's -x plus 0 over our denominator to the third power. So just to reiterate, this came from ax plus b over 3x squared plus 1 to the first, cx plus d over 3x squared plus 1 squared goes away because they're both 0. And then this last one, so that's this one, and then this one was our ex plus f over 3x squared plus 1 to the third power. All right, so let's look at these integrals now. We can see that the first one we can do with a substitution. So if we look at this integral of x over 3x squared plus 1 dx, if we let u be 3x squared plus 1, du is 6x dx, so this becomes 1/6 the natural log of the absolute value of 3x squared plus 1. And then this integral, pull the negative out here, we have x over 3x squared plus 1 cubed. Same substitution, u is 3x squared plus 1, du is 6x dx, so this becomes -1/6, and then we're going to have u to the -2 divided by -2, so that's times -1/2 times 3x squared plus 1 to the -2 power, since it was originally raised to the -3. Then we'll add our constant on. We might want to write that a little more nicely. We'll get 1/6 the natural log of the absolute value of 3x squared plus 1 plus 1 over 12 times 3x squared plus 1 squared plus our constant c. Because this video is not quite long enough yet, we're going to go ahead and do one more example. This one's going to be a little bit different than the ones we've done before in that if you look at it, the numerator is of higher degree than the denominator. This is an improper rational expression, rational function. All of the other ones we've done have had the higher power in the denominator. The reason we need that is so that we can apply things like the natural log to find the antiderivative, or use a u substitution with the derivative in the top, or to use an inverse trig function or something like that. So in order to solve this problem, what we're going to do is start by turning it into a proper rational function by doing a long division. So we're going to divide x cubed plus 2x squared plus 3x plus 4 by the expression, or by the polynomial x squared plus x. And when we do that, x cubed divided by x squared is just x. So, and then when we multiply that out, we get x cubed plus x squared. And now we'll subtract 2x squared, or x cubed minus x cubed is 0. 2x squared minus x squared is 1x squared. And then we bring down our 3x and our 4. And we can divide one more time. X squared by x squared is 1, so we get x plus 1. When we multiply that out, we get x squared plus x. And when we subtract, we get 2x plus 4 as our remainder, which means that our original expression, x cubed plus 2x squared plus 3x plus 4 over x squared plus x can be rewritten as x plus 1, the divisor we just got out of this division, plus 2x plus 4 over x squared plus x. That can be rewritten, and when I say that, I mean this expression here can be rewritten using partial fractions. We have 2x plus 4 over x squared plus x. We're going to factor the denominator. It's 2x plus 4. That's x times x plus 1. Those are both linear. We're going to need to write this as a over x plus b over x plus 1. Each of them only occurs one time in our denominator, so no need for repeated expressions. And so then when we do our multiplication on both sides of that by x times x plus 1, we get that 2x plus 4 is going to equal a times x plus 1 plus b times x. And now we can expand that out to x plus 4. Actually, let's not expand that one out. Let's go ahead and use our choosing smart x's trick. Let's notice that if we let x equal 0, then our left-hand side becomes 4, and that's going to be a times 1 plus b times 0. So we get that a is 4. And then we can do the trick again. We can let x equal -1 on the left-hand side. That's going to give us -2 plus 4, which is 2, equals, this time we have a times 0 plus b times -1. So we get that b must be -2. So now, rewriting, we know that our original integral, which was, again, x cubed plus 2x squared plus 3x plus 4 all over x squared plus x, is going to be equal to our linear piece, which was, let me remind myself, x plus 1. And then we're going to have a over x, so that's 4 over x, plus b, that's -2 over x plus 1. I forgot an antiderivative on this side, so I'll stick that in there. All of that, dx. And now we can think about each of these pieces. So the antiderivative of x is x squared over 2. The antiderivative of 1 is x. The antiderivative of 4 times 1 over x is going to be 4 times the natural log of the absolute value of x. And then the antiderivative of -2 over x plus 1 is going to be -2 times the natural log of the absolute value of x plus 1, plus our constant c. At this point, we have 5, maybe 6 examples of how partial fraction decomposition can help us find antiderivatives. So here we'll just sum up what we've seen. If your original integrand, if the denominator can be factored into simple linear factors, which means they are of the form x minus r and there are no exponents on them, then your decomposition is going to contain a sum of things of the form a over x minus r for each unique factor. If any of those linear factors gets repeated, so it now has an exponent on it, you're going to include in your decomposition every power of that exponent up until you reach it. So in other words, if I had x minus r to the third, I would have to have 3 terms, one containing x minus r to the first, one containing x minus r to the second, and one containing x minus r to the third. And you'll do that for whatever value of m, whatever value your exponent has. If you have irreducible quadratic factors, meaning there's a ax squared plus bx plus c in the denominator that cannot be factored any further, then your numerator becomes linear. So you'll have an ax plus b. If you have powers of that irreducible quadratic factor, you'll proceed like you did for repeated linear factors, except this time keep the numerator as a linear expression rather than a constant. And then finally, if your integrand is an improper rational function, meaning that the numerator has a higher degree than the denominator, before you can proceed with your decomposition, you're going to use a long division and then follow up using a partial fraction decomposition on the remainder over the original divisor.